Welcome back, traveler. Tonight we explore a limit that feels so familiar it almost disappears. The speed of light sounds like a number you were told once, memorized briefly, and then filed away as settled. A constant, a rule. Something physics already figured out so you wouldn't have to think about it again. Light is fast, incredibly fast, and that's where the story seems to end for most people. On everyday scales, that rule feels harmless. Turn on a lamp and the room fills instantly. Look at the sun and it feels present, immediate, now. Even the delay between cause and effect is so small that your brain smooths it over automatically. Light feels less like a messenger and more like a property of reality itself, something that simply is, everywhere, all at once. But here's where that comfort begins to crack. Because the speed of light is not just another fast thing in a fast universe. It behaves less like a speed and more like a boundary, not a technological limit, not a matter of engineering, a structural edge built into how space and time themselves are allowed to work. And once you notice that, the question quietly changes shape. If light has a maximum speed, then information does too. If information has a maximum speed, then cause and effect are no longer guaranteed to line up the way intuition expects. Events stop being universal. Now stops meaning the same thing everywhere. Distance stops being just about space and starts becoming about time. And the universe begins to feel less like a stage and more like a rule book with sharp constraints. If that's true, then faster than light travel isn't just about speed. It would mean messages arriving before they were sent, effects preceding causes, different observers disagreeing on the order of events in ways that cannot be reconciled. It would mean the universe quietly allowing contradictions to exist at the most fundamental level. And that's a much bigger claim than most people realize. By the end of this journey, you won't just know whether something can move faster than light. You'll understand why this question keeps reappearing in science, why it refuses to stay buried, and what the universe seems to protect by enforcing this limit so relentlessly, not as a slogan, as a structure. If you enjoy these late-night explorations, take a second to like the video, subscribe, and leave a comment saying where you're watching from and what time it is. It helps more than you might expect, and it quietly connects this moment to others happening right now across the world. Now, let's begin. For most of human history, speed meant effort. Faster things demanded stronger muscles, better animals, smoother roads, sharper tools. A thrown stone traveled farther if the arm was trained. A horse ran faster if it was bred well. Even early machines followed the same logic. More force in fired more speed out. Nothing in everyday life suggested an absolute limit. Speed felt like something you could always push a little further. Light didn't fit into that picture at first. It wasn't thought of as something that moved at all. For centuries, it behaved more like a condition of vision than a traveler crossing space. You opened your eyes and the world appeared. You looked at the sky and the stars were simply there. If light took time to arrive, that time was so short that no human sense could register it. Intuition quietly classified light as instant. That assumption shaped everything that followed. If light was immediate, then information was immediate. If information was immediate, then the universe shared a single present moment. Cause and effect flowed cleanly forward, synchronized everywhere. Space was a passive container. Time ticked uniformly. Motion happened within that structure, not as something that could distort it. When the first measurement suggested light had a speed at all, it was unsettling but not revolutionary. It was just another fast thing. Extremely fast, yes, but still a thing that moved through space like everything else. Faster ships would one day chase it. Better instruments would one day outrun it. There was no reason to think otherwise. This way of thinking lingered because it worked. On human scales, it predicted outcomes perfectly well. Even on planetary scales, the delay of light barely mattered. Navigation, mechanics, astronomy, all of it functioned as if signals could be exchanged freely and instantly. Nothing broke, nothing protested. The universe seemed cooperative, but beneath that calm surface was a fragile assumption hiding in plain sight, that speeds add the way intuition expects them to. If you walk inside a moving train, your speed combines with the train's speed. If you throw a ball forward from a car, it goes faster relative to the road. This simple stacking of velocities felt universal. Why wouldn't light behave the same way? If a lamp is switched on inside a fast-moving spacecraft, intuition says the light should move faster relative to someone outside. The ship's speed plus the light's speed. Nothing about everyday experience suggests otherwise. This assumption was not careless. It was reasonable. It was almost unavoidable. And for a long time, no experiment contradicted it. That's what makes the eventual fracture so important. The universe did not scream that this intuition was wrong. It whispered. It allowed the mistake to survive for centuries, working well enough to build entire civilizations, before quietly revealing that something deeper was being misunderstood. The real danger in this assumption wasn't that it misjudged light. It was that it treated time and space as separate, rigid backgrounds. Speed was just distance divided by time. Motion happened on top of reality, not as something that could reshape it. Once that framework was accepted, faster than light travel didn't seem absurd. It seemed inevitable. But that raises a problem. Because if light is just another moving thing, then there should exist a frame of reference where it is slower, or faster, or even standing still. And if that were true, then different observers would disagree not just on how fast light travels, but on what counts as cause and effect. The universe would have to choose which observer is right, and that choice never came. Instead, every careful attempt to measure light speed, regardless of direction, motion, or setup, returned the same result. Not approximately, not on average, exactly the same. No matter how fast the observer moved, no matter where the light traveled. At first, that sounded impossible, until you notice what it forces to give way. Because if the speed of light does not change, then something else must. And whatever that something is, it cannot be small. The first real trouble didn't arrive as a dramatic contradiction. It arrived as stubborn consistency. Light behaved too well. No matter how carefully observers tried to catch it speeding up or slowing down, it refused. The result was always the same. Direction didn't matter. Motion didn't matter. The universe seemed oddly protective of that number. At first, this was framed as a technical problem. Perhaps the instruments weren't sensitive enough. Perhaps subtle effects were being missed. Perhaps the medium carrying light behaved strangely. The idea that light might require a substance to move through, something invisible but physically real, felt comforting. If sound needs air, why wouldn't light need its own carrier? This imagined medium was given a name, but more importantly, it was given a job. It was supposed to provide the missing reference frame, a cosmic background that stayed still while everything else moved through it. If Earth was drifting through this medium, then light traveling in different directions should arrive at different speeds, just like swimming upstream versus downstream. The logic was flawless. The universe simply refused to cooperate. Experiments were set up with extreme care, designed to detect even the slightest difference in light's behavior, depending on direction or motion, mirrors, beams, rotations, repetitions. The expectation was modest. No one was trying to overturn reality. They were trying to measure a small discrepancy, a faint drift, something to confirm that the framework made sense. Nothing appeared. No matter how the apparatus was oriented, no matter how Earth moved through space, light behaved as if the experiment were always at rest. The result wasn't almost zero. It was zero within measurement limits, over and over again. This wasn't just surprising, it was structurally disturbing. Because if Earth were moving through a medium, that motion should have shown up somewhere. The absence of any detectable effect implied one of two things. Either Earth was always coincidentally at rest relative to the medium, an implausible coincidence on cosmic scales, or the entire concept of the medium was wrong. That realization marked a quiet turning point. Not a sudden revolution, but a growing unease. The old intuition still worked for almost everything, but now it had a crack running through it, a place where explanation had been patched rather than understood. The deeper problem was this: motion had lost its anchor. If there was no universal background, then speed could no longer be defined absolutely, only relatively. But light refused to participate in that relativity. It behaved as if its speed was the same for everyone, regardless of how they moved. That wasn't just odd, it was incompatible with how velocities were supposed to add. If you chase a beam of light, intuition says you should see it slow down. If you move toward it, you should see it speed up. But experiments said neither happened. Light behaved as if it didn't care who was watching. At first, that sounded like a flaw in measurement. Then it began to sound like a flaw in assumption. Because if light speed is the same for all observers, then observers themselves cannot agree on distances and durations. Something had to give. Either space was flexible, or time was, or both. That's where the danger really entered the picture. Up until this point, the question of faster-than-light motion still felt open. If light was just another fast thing, then surpassing it was a matter of technology. But once light became a fixed speed for everyone, the meaning of faster changed. It was no longer about beating a runner in a race. It was about breaking the rules that defined the race itself. If you could outrun light under those conditions, you wouldn't just arrive early, you would arrive out of order. Different observers would disagree about what happened first. Effects could precede causes. Messages could arrive before they were sent. This wasn't philosophy intruding into physics. It was physics cornering philosophy. The old intuition had treated space and time as a neutral stage. Light's behavior suggested they were active participants, flexible, observer-dependent, and tightly constrained by a single, stubborn number that refused to budge. Most people stopped the story here, satisfied that nothing goes faster than light is simply a rule, but rules can be bent, bypassed, engineered around. This wasn't a rule, it was a symptom, a clue pointing toward a deeper framework that had not yet been articulated. And that raises the next problem. If light speed is fixed not because of engineering limits, but because of how space and time themselves are stitched together, then asking whether something can go faster than light becomes a very different question. It stops being about speed and starts being about structure. The true turning point did not come from building a faster machine or a more delicate detector. It came from asking a quieter question. What if the problem isn't light at all? Up to this moment, Every attempt had treated space and time as fixed backgrounds. Light was the thing being measured, chased, trapped, compared. But every experiment that failed did so in the same peculiar way. Light speed stayed the same, while everything else, distances, durations, expectations, refused to line up cleanly. That pattern mattered. If a single phenomenon behaves consistently across every frame of motion, all descriptions around it strain and contort, then the phenomenon may not be the anomaly. The framework might be, this is where intuition finally snaps. Imagine two observers moving relative to each other, each carrying identical clocks and rulers. Under the old picture, they should disagree about speeds, but agree about lengths and durations. Time ticks the same everywhere. Space stays rigid. Light, like a thrown ball, should obey those rules, but the experiments demanded the opposite. If both observers measured the same speed of light, then they could no longer share the same measurements of space and time. Something had to stretch, something had to bend, and the universe made a choice. Lengths became negotiable. Time became flexible. The speed of light remained absolute. This was not a tweak. It was a reordering of priorities. Space and time, once treated as the stage on which physics happened, were demoted to actors themselves. They could change depending on motion. They could disagree between observers. And yet the underlying laws would remain consistent for everyone. At first, this idea felt absurd. Time slowing down, lengths shrinking. These sounded like mathematical tricks, not physical realities. But the predictions were precise. And more importantly, they were testable. And they worked. Clocks moving relative to one another ticked at different rates. Objects in motion measured shorter along the direction of travel. Events that seemed simultaneous in one frame were separated in another. None of this violated causality as long as nothing outran light. That caveat is crucial, because within this new framework, faster-than-light motion wasn't merely difficult, it was poisonous. It shattered the careful balance that kept cause before effect. It allowed different observers to reorder events in ways that made contradiction unavoidable. This is where the question, is there something faster than light, reveals its teeth. It is not asking whether a particle can go very fast. It is asking whether the universe is willing to tolerate causal loops, whether it allows information to arrive before it is sent, whether reality is comfortable contradicting itself depending on who is watching. So far, the answer has been a quiet, consistent no. Every confirmed observation aligns with the same rule. As objects approach the speed of light, the cost of going faster rises without bound. Not because engines fail, but because space-time itself resists. Time dilates, energy demands explode. Motion transforms the very quantities you'd need to measure success. The limit is not enforced by friction or material strength. It is enforced by geometry. That distinction matters because it poses many intuitive escape routes. You cannot push harder. You cannot take a shortcut through ordinary space. You cannot stack velocities and hope light doesn't notice. The structure adapts to prevent the violation. At first, this sounds like a cosmic conspiracy, but it's simpler than that. The universe is not protecting light. It is protecting consistency. Every attempt to imagine faster-than-light motion within this framework leads to the same breakdown. Signals outrun causes. Observers disagree on what happened first. Paradoxes stop being philosophical puzzles and become unavoidable predictions. This doesn't mean imagination stops. It means imagination has to change shape. Instead of asking how to outrun light, the question shifts toward whether there are ways to rearrange space itself. Whether the limit applies to motion through space, but not to space as an object of geometry. Whether shortcuts and expansions or global rearrangements could exist without local violations. And here's where it gets strange again, because some of those ideas are not forbidden outright. They sit in a gray zone where mathematics allows them, but nature has not yet confirmed them. They flirt with the boundary without crossing it. They promise speed without motion, distance without travel, arrival without departure. And that raises the most dangerous possibility of all. What if the universe doesn't forbid faster than light effects outright, but only forbids them in very specific ways? That question doesn't break the framework. It tests it, and that's where the story goes next. What most people imagine when they hear faster than light is speed, a number, a race. Something moving through space so quickly that it overtakes a beam of light the way a jet overtakes a propeller plane. But by the time physics reached the turning point we just crossed, that intuition was already obsolete. The real barrier is not speed through space. It is the structure of space and time themselves. Once that clicks, the question transforms. It stops being, can something move faster, and becomes, what does faster even mean when time itself is negotiable? This is where the conversation usually derails, because our language is built for a world where space is fixed and time flows uniformly. We talk about before and after as if they were absolute. We talk about distance as if everyone agrees on how far apart 2 points are. But relativity dismantles that comfort. Different observers do not share the same measurements. They do not even share the same present. And that creates a strange loophole, not a loophole in physics, but in intuition. Consider two events separated by a vast distance in space. In everyday life, we assume there is a clear answer to which one happened first. But relativity shows that for events far enough apart, the order depends on how you're moving. For one observer, event A happens before event B. For another, B happens before A. Neither is wrong. The universe allows both descriptions simultaneously. This does not violate causality because neither event can influence the other. No signal traveling at or below light speed can connect them. They exist in what physicists call a space-like separation, a region where before and after lose their universal meaning. That detail matters deeply, because it tells us something subtle but powerful. The universe does not forbid different observers from disagreeing about time. It only forbids them from disagreeing in ways that allow cause and effect to flip. Light is the referee. Anything slower than light is trapped inside its causal cone. Anything faster would step outside it, into a realm where contradictions are no longer avoidable. Where an effect can precede its cause for some observers, but not others. Where the universe would be forced to decide which perspective is real, and the universe refuses to do that. So when people ask whether something faster than light could exist, the real question is whether the universe tolerates ambiguity without contradiction, whether it allows disagreement without collapse. So far, every confirmed observation says no. But now comes the uncomfortable part. The equations of physics, especially those describing space-time itself, do not slam every door shut. They leave narrow corridors open, not for objects racing through space faster than light, but for space itself, behaving in ways that mimic it. This distinction is often missed, and when it is missed, confusion explodes. You cannot move through space faster than light. But space itself is not required to behave like a rigid grid. And that is not speculation. It is already happening. Right now, distant galaxies are separating from us at effective speeds greater than the speed of light. Not because they are moving through space rapidly, but because space between us and them is expanding. The metric itself is stretching. Light emitted today from beyond a certain distance will never reach us, no matter how long we wait. Nothing locally violates the speed limit. No particle outruns a photon nearby, yet globally, separation grows faster than light can bridge. This is not a loophole. It is a feature, and it tells us something dangerous. The speed of light is not a limit on change. It is a limit on influence. That realization opens the door to the most provocative ideas ever proposed in physics, not because they are likely to be real, but because they expose exactly where the boundary lies. One such idea is the notion of reshaping space-time itself, compressing it in front of an object and expanding it behind. Locally, nothing exceeds light speed. Globally, the destination approaches faster than light would normally allow. Mathematically, such configurations exist. They are not forbidden by the equations that govern space-time curvature. On paper, you can write down solutions where a region of space moves effectively faster than light relative to distant observers. But mathematics is not permission. It is only a map. The cost of these configurations is extreme. They require forms of energy that behave unlike anything ever observed. Negative energy densities, exotic stress energy conditions, things that violate every classical intuition we have about matter. So far, every known physical system refuses to provide what these solutions demand. And that refusal matters, because it suggests a pattern. Whenever physics allows a structure that threatens causality, it demands a price so steep that nature appears unwilling to pay it. The universe doesn't shout impossible. It whispers unaffordable. The same pattern appears again when people point to quantum phenomena and say, "Look, instantaneous effects." Entanglement seems to connect particles across vast distances instantly, as if information itself ignores the speed limit. But this is another illusion born from classical thinking. Entanglement creates correlations, not messages. You cannot use it to send information faster than light. You cannot choose the outcome. You cannot control what the distant observer receives. Only when classical signals, limited by light, are exchanged, does the correlation become visible. Again, the universe allows mystery without allowing contradiction. Everywhere we look, this boundary holds. Effects may appear strange, delayed, stretched, or reordered, but never in a way that lets cause outrun effect in a controllable way. And that tells us something profound about what the speed of light really is. It is not a wall built around photons. It is the skeleton of logical order itself. If something truly traveled faster than light, not in appearance, not by geometry, not by expansion, but as a controllable signal, then the universe would lose the ability to define before consistently. Physics would fracture into observer-dependent contradictions. Prediction would fail. History itself would become ambiguous, and the universe does not tolerate that. So the question, is there something faster than light, is not naive. It is existential. It is asking whether reality is built on coherence. or whether coherence is just a local illusion we haven't broken yet. So far, coherence is undefeated. But the story does not end here, because there are still experiments, still anomalies, still ideas that sit uncomfortably close to the line. Still questions about whether the limit is absolute everywhere, or whether it emerges from deeper rules we do not yet fully understand. And once you see the speed of light, not as a number, but as a guardian of causality, a final, unsettling thought emerges. If the universe ever allowed something faster, even once, then reality itself would change shape, and that makes the next question unavoidable. What would it take to break that limit, and what would break with it? There is a moment in this story where speed stops being the problem. Up to this point, it feels natural to think in terms of motion, faster engines, shorter travel times, beating a cosmic record. That instinct comes from living in a world where time feels universal and space feels fixed. You throw a ball, it moves. You drive faster, you arrive sooner. Everything stacks neatly, but relativity quietly dismantles that simplicity. Once you accept that different observers do not share the same clock, the same ruler, or even the same definition of now, speed through space loses its privileged status. What matters is not how fast something moves, but how events relate to one another across spacetime. And this is where the idea of faster than light travel stops being about motion and starts being about chronology. Imagine two events separated by a vast distance, a light turning on in one galaxy, a detector clicking in another. In everyday thinking, it feels obvious that one must happen before the other. But relativity says that if no signal traveling at or below the speed of light connects them, the universe does not enforce an order. Different observers, moving differently, will disagree about which came first. Both descriptions are valid. Neither can claim authority. This is not philosophical wordplay. It is a measurable feature of reality. The universe only becomes strict when causation is involved. The moment one event can influence another, the speed of light steps in and draws a boundary. Inside that boundary, cause must precede effect. Outside it, the universe allows ambiguity. This is why the speed of light is not just fast, it is decisive. Now consider what would happen if a signal could travel faster than light in a controllable way, not as a trick of geometry, not as expansion, not as appearance, but as information that can be sent intentionally. The moment that happens, ambiguity becomes contradiction. Because now, an event that is an effect in one frame becomes a cause in another. A message can be received before it is sent, depending on how you are moving. And once that door opens, there is no way to close it selectively. This is where paradoxes stop being thought experiments and start becoming unavoidable consequences. You could send a warning to your own past. You could prevent an action that caused the message you just received. You could create loops where an effect has no origin. Not because of bad storytelling, but because space-time itself would no longer agree on order. The universe is astonishingly tolerant of weirdness. It allows time to slow down. It allows space to contract. It allows simultaneity to fracture. But it is intolerant of contradiction. That intolerance shows up everywhere we look. Whenever physicists try to write down theories that allow faster-than-light signals, the same disease appears. Causality violations, closed time-like curves, inconsistent histories, predictions that depend on who is asking. not on what is happening. The equations don't just misbehave slightly, they unravel. And this is where something important becomes clear. The speed of light is not a speed limit in the way sound has a speed limit. It is not about resistance, friction, or effort. It is not that the universe struggles to go faster. It is that the universe uses this limit to protect logical structure. That's why even particles with no mass are forced to move at exactly this speed, not slower, not faster, exactly. Because allowing a massless particle to move slower would imply a frame where it is at rest, which would destroy the symmetry of the laws governing electromagnetism. Allowing it to move faster would destroy causality. The value itself matters less than the role it plays. Now pause for a moment and notice how far this is from intuition. Nothing in daily life prepares you for a universe where the maximum speed is also the maximum speed of cause and effect, where motion is secondary to information, where the structure of time bends to preserve consistency. And yet, every experiment we have ever run agrees with this picture. Particles accelerated to extreme energies refuse to cross the barrier. The closer they get, the more energy is required not linearly but catastrophically. Each increment demands more than the last, as if the universe is asymptotically approaching a rule it will not break. This is not an engineering problem. No clever design bypasses it. No material solves it. The limit is not in the machine. It is in spacetime itself, which raises a disturbing thought. If the universe is so careful to prevent faster-than-light influence, why do the equations even flirt with it? Why do solutions exist that seem to bend the rules without technically breaking them? This is where physics becomes subtle instead of rigid. The universe distinguishes between local behavior and global geometry. Locally, no object outruns light. No observer sees causality reversed in their immediate neighborhood. But globally, spacetime can be arranged in ways that produce surprising outcomes without violating local laws. This is how expansion works. This is how horizons form. This is how distant regions slip beyond reach without anything locally misbehaving. The universe allows shortcuts in geometry, but not in influence. And that distinction is everything, because it means that the question, is something faster than light, is incomplete. The deeper question is whether influence itself can outrun the structure that defines before and after. So far, every serious attempt to make that happen has failed. Not because physicists lack imagination, they have no shortage of it, but because every such attempt runs into the same wall, the collapse of predictability. And predictability is not optional. Without it, science stops working. Memory stops making sense. Identity dissolves. The idea of a consistent universe evaporates. So the speed of light remains undefeated, not by force but by necessity. But we are not done, because there is one more layer to this story. And it is the most unsettling one of all. What if the speed of light is not fundamental but emergent? What if it arises from deeper rules that we have not yet uncovered? And if so, what happens near the edges of those rules, at extremes of energy, curvature, or scale? That question has not been answered, and that is where the story turns from certainty to tension, because if the limit ever breaks, it will not do so gently. It will break reality with it, and that is where we go next. There is a quiet reason the idea of something faster than light refuses to leave the human imagination, even after more than a century of careful physics. It is not just curiosity. It is discomfort. The speed of light feels less like a discovery and more like a restriction imposed on the universe itself. And restrictions invite resistance. We are creatures who evolved by overcoming limits. Rivers were crossed. Mountains were climbed. Oceans were mapped. Every boundary we encountered eventually gave way to a method, a tool, or a new way of thinking. So when physics presents a boundary that claims not just to slow us down, but to define what can and cannot influence reality, the instinct is not to accept it. The instinct is to look for cracks. At first glance, that instinct seems reasonable. After all, the speed of sound once felt absolute. For centuries, no one imagined outrunning it. Then technology improved, engines grew stronger, and the barrier fell with a shockwave. It is tempting to project that story forward and assume light is simply the next wall waiting to be broken. But this analogy hides a critical difference that only becomes visible when you stop thinking about speed as motion and start thinking about speed as structure. Sound is a phenomenon that exists inside space and time. It depends on a medium. It can be slowed, distorted, or stopped entirely without changing the underlying rules of reality. Light is not like that. Light does not merely move through space-time. It helps define space-time. The speed of light appears not as an accident of materials or forces, but as a conversion factor between space and time themselves. Change that speed, and you are not improving transportation. You are altering the grammar of the universe. This is where the human mind begins to struggle, because our intuition treats space and time as separate containers. Space is where things are. Time is when things happen. Motion connects the two, but relativity dissolves that separation. Space and time are woven together so tightly that they can trade roles depending on how you move. Distance can become duration. Duration can become distance. And the speed of light is the stitching that keeps the fabric coherent. Once you accept that, the idea of faster-than-light motion stops being a question of engineering and becomes a question of consistency. You are no longer asking whether something can go faster. You are asking whether cause can outrun effect. To see why that matters, imagine a simple scene. A flash of light leaves a distant star. Somewhere else, long afterward, a telescope detects it. In your everyday understanding, this feels straightforward. The flash happened first, the detection happened later. But relativity reveals that this ordering is not universal. Observers moving differently will disagree on the timing. Some will say the detection happened earlier than you think, others later. None of them are wrong. The universe allows this disagreement because no signal travels between the events faster than light. No causation is violated. Ambiguity is permitted. Now imagine replacing that flash of light with a message that travels faster than light. The moment you do, ambiguity becomes contradiction. Observers will not just disagree about timing, they will disagree about cause itself. In some frames, the message arrives before it is sent. In others, it does not. The universe can tolerate disagreement, but it cannot tolerate a situation where an effect erases its own cause. This is not a storytelling problem. It is a structural one. Physics is not built on narrative preference. It is built on self-consistency. When equations predict outcomes that depend on the observer in ways that destroy logical order, something has gone wrong at a fundamental level. This is why physicists treat faster-than-light information with suspicion bordering on hostility. not because it is inconvenient, but because it breaks the scaffolding that allows predictions to exist at all. Without a stable notion of causality, experiments lose meaning. Memory loses meaning. Even identity becomes questionable, because the sequence of events that define before and after can no longer be trusted. Yet despite this, the universe itself seems oddly comfortable playing near the edge of this rule. It allows space to expand so quickly that distant galaxies recede from us faster than light, not because they are moving through space that fast, but because space itself is stretching between us. It allows quantum correlations that appear instantaneous, even though they cannot be used to send information. It allows horizons where events become forever unreachable, even though nothing locally exceeds the speed limit. These are not loopholes. They are reminders that the universe enforces its rules locally, not globally. No object outruns light in its own neighborhood. No signal locally reverses cause and effect. The deeper structure remains intact. This distinction is subtle, and it matters more than it first appears. Many proposed ideas that claim to break the light barrier rely on confusing local motion with global geometry. They imagine folding space, tunneling through shortcuts, or exploiting exotic conditions where the rules might bend. Some of these ideas are mathematically interesting. Very few are internally consistent under extreme assumptions, but all of them face the same obstacle when confronted with reality: the need to preserve causal order everywhere, not just where it is convenient. Even hypothetical constructs like warp bubbles or traversable shortcuts must answer the same question. Can information be sent in a way that allows an effect to occur before its cause in any frame? If the answer is yes, the theory collapses. If the answer is no, the apparent speed advantage vanishes. This is why the speed of light feels less like a fence and more like a lock. It is not there to keep us from moving fast. It is there to keep the universe from contradicting itself. And this leads to a deeper unease. If the speed of light is so central, why does it have the value it does? Why not faster? Why not slower? Is it truly fundamental? Or is it an emergent feature of something deeper that we have not yet uncovered? That question has driven decades of speculation. Some theories suggest that at unimaginably small scales, spacetime may have a granular structure, and that the smooth fabric we experience is only an approximation. Others propose that the speed of light might change under extreme conditions, such as near singularities or during the earliest moments of the universe. These ideas are not dismissed outright, but none have yet produced evidence that the causal structure of reality can be violated. What we find instead is something more unsettling. The closer we look, the more the universe appears to be organized around protecting relationships rather than objects. Events matter more than things. Connections matter more than locations. And the speed of light is the rule that governs those connections. So when we ask whether something can be faster than light, we are not really asking about speed at all. We are asking whether reality can survive the loss of its own order. And so far, every answer we have points to the same conclusion. The universe would rather contort space, stretch time, and bend intuition than allow cause and effect to lose their sequence. But that conclusion is not the end of the story. Because at the edges of physics, where gravity becomes extreme and quantum rules dominate, our confidence begins to falter. There are hints, tensions, unanswered questions. Not proof of violation, but pressure. Pressure on the idea that our current understanding is complete. And it is in that pressure, not in fantasy, not in wishful thinking, that the most dangerous questions remain waiting. That is where we are headed next. To understand why faster-than-light motion threatens time itself, you have to abandon the comforting idea that the past is a fixed place behind you, and the future a fixed place ahead. In everyday life, time feels like a river flowing uniformly forward, carrying everything with it. Events line up neatly. Causes come first. Effects follow. Nothing ever arrives before it is sent. This intuition is so deeply ingrained that it feels impossible to imagine it failing. Yet relativity does not merely suggest that time flows differently. It demonstrates that time does not flow at all, in the way we instinctively believe. In the relativistic picture, the universe is not a sequence of moments, but a four-dimensional structure where every event already exists within spacetime. What separates past from future is not an absolute boundary, but a perspective-dependent slicing of that structure. Different observers moving differently carve spacetime into nows along different angles. These slices do not agree. They cannot agree. And yet, under normal circumstances, this disagreement remains harmless because no signal is allowed to travel in a way that forces one observer's future to invade another observer's past. This protective rule is encoded geometrically through what physicists call light cones. You do not need the mathematics to grasp the idea. Imagine a single event, a flash, a click, a collision. From that point, light spreads outward in all directions, forming a cone through spacetime. Everything inside that cone can be influenced by the event. Everything outside it cannot. The cone defines the limits of causality itself. Within this structure, the universe allows disagreement without contradiction. Two observers may argue about when something happened, but they will never disagree about whether one event could have caused another. The ordering of cause and effect remains intact because the light cone acts as a universal referee. It does not care about opinions. It enforces boundaries. The moment you introduce faster-than-light information, those boundaries dissolve. At first, this may sound abstract, but its consequences are brutally concrete. Suppose a signal is sent faster than light from one location to another. In the sender's frame, the message leaves first and arrives later. Nothing unusual seems to happen. But for an observer moving fast enough relative to the sender, the geometry of space-time rearranges itself. The arrival of the message can now occur before its emission. Not metaphorically, not approximately, literally. This is not a trick of language. It is a direct outcome of how space-time transforms between observers. The faster-than-light signal slips outside the light cone, and once it does, it loses any consistent temporal ordering across frames. Cause and effect swap places depending on who is watching. One such inversion might be tolerable if it remained isolated. But physics does not allow isolation. Events chain together. Information propagates. Once you permit a single violation, you open the door to closed causal loops, sequences of events that circle back on themselves. In such a loop, a message can be sent that prevents its own transmission. An effect can erase its own cause. A decision can be influenced by information that depends on the decision itself. The universe becomes logically unstable. This is not science fiction exaggeration. These loops appear naturally when faster-than-light signaling is combined with ordinary motion. No exotic machinery is required, just relative velocity and a willingness to let information outrun light. The unsettling part is how little you need to break everything. You do not need infinite speed. You do not need time machines. You only need something that arrives slightly too early in the wrong frame. The rest collapses under its own weight. This is why physicists say that faster-than-light communication is equivalent to time travel. Not because it allows dramatic journeys to the past, but because it allows influence without temporal protection. The difference between sending a message yesterday and sending a message faster than light is thinner than intuition suggests. And yet, the universe itself seems disturbingly close to allowing such behavior. Quantum entanglement, for example, creates correlations that appear to update instantaneously across vast distances. Measure one particle, and the state of its partner is fixed immediately, no matter how far away it is. This has tempted many into believing that information is traveling faster than light behind the scenes, but this temptation dissolves under scrutiny. Entanglement does not transmit usable information. It does not allow control. It preserves the light cone's authority, even while challenging our classical notions of locality. Similarly, the expansion of the universe allows galaxies to recede from us faster than light, without violating causality, because no information is traveling through space faster than the limits. Space itself is stretching. The local rules remain unbroken. These examples matter because they reveal a pattern. Whenever something seems to approach or exceed the speed of light, it does so in a way that preserves causal structure. The universe bends, but it does not snap. This makes proposals for faster-than-light travel especially suspect. They must do more than move objects efficiently. They must answer a deeper question. How do they prevent causal loops? How do they protect the ordering of events across all frames? Most proposals fail quietly at this stage. They rely on assumptions that break down under transformation. They hide contradictions inside coordinate choices. They work only if observers agree on time, which relativity explicitly forbids. Even speculative ideas that manipulate space-time geometry itself, compressing space in front, expanding it behind, run into the same wall. Unless the geometry is constrained in impossible ways, the resulting paths allow signals to slip outside light cones. The paradoxes turn, not as philosophical curiosities, but as mathematical certainties. This is why the speed of light feels so stubborn. It is not guarding motion, it is guarding meaning. Without it, the concept of before and after loses coherence. History becomes frame-dependent, memory becomes unreliable, prediction becomes impossible. And yet, this creates a stranger symmetry. The universe allows us to approach the speed of light arbitrarily closely. Particles can reach velocities so near the limit that time nearly stops for them. Distances nearly vanish. The rules stretch to extremes, but the final step is never taken. This asymmetry suggests that the speed of light is not merely a practical limit, but a boundary condition of reality itself. A line that can be approached but not crossed without dissolving the structure that makes approach meaningful. Still, boundaries invite pressure, and pressure builds questions. If causality is so fragile, why does the universe flirt with violations at all? Why allow entanglement? Why allow horizons? Why allow frames to disagree so violently about time? Perhaps the deeper truth is not that the universe is protecting causality, but that causality is emerging from something even more fundamental, something we have not yet fully understood. And that possibility opens a door. Because if causality is emergent, not absolute, then the question is no longer whether something can go faster than light. The question becomes whether the universe can tolerate exceptions, and under what conditions. That is where the next layer of the story begins. At this point, it would be tempting to declare the case closed. Faster-than-light motion destroys causality. Causality is fundamental. Therefore, nothing outruns light. Clean, elegant, final. But nature rarely respects arguments that feel this need. Instead, it leaves behind clues that complicate the story, places where distance collapses, where separation becomes ambiguous, where faster than light appears in disguise without ever breaking the rules. One of the most unsettling examples is the expansion of the universe itself. On sufficiently large scales, distant galaxies are receding from us faster than light, not metaphorically, not approximately, literally. Their recession speeds exceed the speed of light and increase the farther away they are. This sounds like a direct violation of everything we've just established, until you notice what is actually moving. The galaxies are not racing through space. Space is stretching between them. This distinction changes everything. The speed limit imposed by relativity applies to motion through space, not to the expansion of space itself. Locally, every observer still measures light moving at the same speed, and no signal outruns it. Globally, however, distances can grow faster than light can traverse them. Regions of the universe slip beyond causal contact, not because something moved too fast, but because the stage itself expanded underneath the actors. This creates cosmic horizons, boundaries beyond which events can no longer influence us, not even in principle. Light emitted today from beyond a certain distance will never reach us, no matter how long we wait. Not because it is blocked, but because the space it must cross keeps growing faster than it can travel. Here, faster-than-light separation exists without faster-than-light communication, and that pattern is telling. The universe seems perfectly comfortable creating situations where things appear to outrun light, as long as no usable information crosses the boundary. Distance may explode, connectivity may fail, visibility may vanish, but causality remains intact. The same logic appears again in the early universe, during a period known as cosmic inflation. In a fraction of a second, space expanded so violently that regions once microscopically close were flung far beyond each other's horizons. The separation rate vastly exceeded the speed of light, yet once again, nothing locally violated relativity. No signal outran light. The geometry simply changed too quickly for light to keep up. This raises an uncomfortable realization. The speed of light is not the fastest thing. It is the fastest relationship. It defines how cause and effect propagate locally, not how the universe rearranges itself globally. That subtlety matters because it explains why many proposed loopholes feel so seductive and why they ultimately fail. Consider hypothetical shortcuts through spacetime. Tunnels, folds, compressions. If space can stretch faster than light, why can't it also fold in a way that brings distant points together? Why not create a path that is locally slow but globally short? On paper, some solutions to Einstein's equations allow exactly this. They describe geometries where two distant regions are connected by a narrow throat, reducing travel time without exceeding local speed limits. No engine breaks the light barrier. No particle outruns light in its neighborhood, and yet something always goes wrong. These geometries demand exotic conditions, negative energy densities, violations of stability, configurations that collapse faster than they can be used. When examined carefully, they tend to either self-destruct or reintroduce causal paradoxes elsewhere in the structure. The universe appears to tolerate these solutions mathematically, but not physically. Again, the pattern repeats. Nature allows ideas to exist at the edge, but refuses to let them function. Quantum mechanics provides another false glimmer of superluminality. Entangled particles exhibit correlations that appear instantaneous across arbitrary distances. Measure one, and the other's state is immediately constrained. The temptation to call this faster-than-light communication is strong and deeply misleading. The correlations do not transmit controllable information. They do not allow signaling. They preserve the causal structure, even as they challenge classical intuitions about separateness. The universe permits non-local relationships, but not non-local messages. This distinction is the key to understanding why faster-than-light effects keep appearing without ever becoming tools. The universe seems to care less about speed itself and more about influence, about what can be used to cause change, about what can carry intention. Anything that might allow a decision made here to alter an outcome there before light could connect them is forbidden. Anything that merely reshuffles geometry, correlations, or visibility without enabling control is allowed. This is why the speed of light feels less like a wall and more like a filter. It does not block everything that moves fast. It blocks everything that could undermine consistency. And consistency, it turns out, is expensive. Every time the universe flirts with faster-than-light structure, it pays a price elsewhere. Horizons appear. Regions become unreachable. Information is lost behind boundaries. The cosmos fragments into causally isolated islands. This raises a deeper, more unsettling possibility. Perhaps the universe is not enforcing a speed limit to preserve causality. Perhaps causality is emerging because the universe enforces deeper constraints, constraints on information, stability, and self-consistency. The speed of light may simply be the most visible consequence of those constraints. If that is true, then asking whether something can go faster than light may be the wrong question entirely. The better question becomes, what is the universe willing to sacrifice to keep cause and effect intact? So far, the answer has been almost anything else. It will stretch space until galaxies disappear. It will entangle particles across cosmic distances while forbidding communication. It will permit solutions that exist mathematically but collapse physically. It will allow horizons, inflation, isolation, and loss, all to prevent paradox. And yet, every sacrifice leaves a scar, a place where intuition fails, a boundary that feels arbitrary, a rule that invites one more test. Which brings us uncomfortably close to the final edge of the question. Because if faster-than-light motion is forbidden not by speed, but by consistency, then the real mystery is not whether something outruns light. It is whether the universe has ever broken its own rule. And what would happen if it did? That is where the story turns from limits to consequences. Long before light became a number, a constant chase or a boundary etched into equations, it was already a psychological limit. Humans have always lived inside distances that felt unfair. The next valley took days to cross. The next continent took months. News arrived too late to matter. Help arrived after it was no longer needed. For most of history, the speed of information was the speed of a horse, a ship, or a lung struggling against exhaustion. Every major leap in civilization has been, at its core, an argument with distance. Roads compress land, ships flatten oceans, telegraph wires collapse continents into moments, radio dissolves borders entirely. Each time, the same illusion appears. The world feels smaller, more connected, more controllable. And each time, a new ceiling quietly forms above us. When sound was broken, it felt like a betrayal of nature. Shock waves, broken windows, bodies pressed into seats. Yet the world did not unravel. Faster travel became routine. The impossible became boring. The lessons seemed clear. Limits are temporary misunderstandings. So when physics presented the speed of light as a boundary, it felt less like a discovery and more like a challenge. Because light is not just fast, it is inconveniently fast. Too fast to beat by brute force, too woven into reality to sidestep casually. Unlike sound, light does not depend on a medium you can push harder against. Unlike ships or planes, it does not move through something that yields. Light moves through the structure of space-time itself, and yet the human response has never been acceptance. It has been negotiation. What if we don't outrun light, but outsmart it? What if we take a shortcut? What if the universe hit a loophole we just haven't found yet? These questions are not driven by equations. They are driven by loneliness, by impatience, by the ache of separation. The stars are close enough to see, yet far enough to remain unreachable. The universe invites curiosity while denying contact. Faster than light travel promises not speed, but intimacy, the end of isolation. This emotional undercurrent matters because it explains why faster than light ideas keep returning, even after being dismissed. They return because the problem they address is not technical. It is existential. If nothing can outrun light, then the universe is fundamentally fragmented. Civilizations are trapped in their local bubbles. The night sky becomes a museum rather than a map. We can observe history, but never participate in it. We can see galaxies die without ever touching them. That realization is deeply uncomfortable. And so, again and again, thinkers have attempted to bend the rules just enough to soften that outcome. Not to destroy causality, but to negotiate with it, to ask whether the universe might allow one exception, one carefully engineered escape hatch. These attempts often begin with optimism. If light defines the maximum speed of information, then perhaps information isn't what matters. Perhaps mathless signals are special cases. Perhaps geometry can be persuaded to help. Perhaps time itself can be persuaded to cooperate. But each proposal eventually runs into the same invisible wall, not a force and not a barrier, but a contradiction. Every faster-than-light scheme, when examined closely, allows something subtle but devastating. Influence without order, effects without agreed-upon causes. Events whose sequence depends on who is watching. Not chaos in the explosive sense, but a quiet, logical decay. The universe appears to reject this not violently, but absolutely. This is why the speed of light feels different from previous limits. Breaking sound did not threaten the meaning of before and after. breaking light does. It challenges the idea that the universe tells a single story. Without a shared order of events, reality fractures into incompatible narratives. One observer's past becomes another's future. One cause becomes another effect. The universe stops agreeing with itself, and agreement, it seems, is non-negotiable. What makes this especially striking is how close nature lets us get. Relativity does not merely say no. It invites you to approach the boundary asymptotically. Objects can move arbitrarily close to the speed of light. Time can slow dramatically. Length can shrink. Energy can grow without obvious bound. You are allowed to lean against the wall, just never pass through it. This design choice feels deliberate, almost pedagogical, as if the universe wants you to understand why the limit exists, not merely obey it. And yet, understanding does not dissolve the frustration. If anything, it sharpens it, because now the question is no longer whether something can move faster than light. It is whether the universe could ever permit a different kind of connection, one that satisfies our need for reach without tearing causality apart. Is there a form of faster that does not mean speed? A form of closeness that does not mean travel? A way to touch the distance without arriving early? These questions sit uncomfortably between physics and philosophy, between equations and longing. And they hint that the final answer may not be about motion at all. It may be about what kind of universe we live in, and what kind it refuses to be. That realization pulls us toward the final layer of the problem, where the speed of light stops looking like a technical constraint and starts looking like a statement. Not about how fast things can go, but about how reality chooses to remain whole. Once the emotional hunger for faster-than-light answers collides with the rigidity of causality, physics does something unexpected. It doesn't retreat. It pivots. Instead of asking how to outrun light, it asks whether the question itself is misframed, whether speed is the wrong variable, whether motion is the wrong concept, because relativity does not forbid everything that looks faster than light. Earth forbids only one very specific thing: information locally outrunning light through spacetime. And that distinction opens a narrow, unsettling corridor of possibilities. The first crack appears when you stop thinking of space as static. In everyday life, distance feels passive, a gap between 2 points, something you cross, not something that changes. But in relativity, space is not a backdrop. It is dynamic. It stretches. It curves. It evolves. And crucially, it is not constrained by the same speed limits as objects moving within it. This is not a loophole invented to dodge the rules. It is a consequence of how the universe behaves. Galaxies, for example, are not flying away from each other through space at extreme speeds. Space itself is expanding between them. On sufficiently large scales, this expansion can separate regions faster than light could ever traverse. Not because anything is moving too fast, but because the distance itself is growing. This is not hypothetical, it is observed. There are galaxies so distant that light emitted from them today will never reach us, no matter how long we wait. The space between us and them expands faster than the light can close the gap. They are not behind at all. They're receding on a conveyor belt that outruns every photon they send. At first, this sounds like the limit has been violated, but it hasn't. Locally, light still obeys the speed limit. No signal outruns it in its immediate neighborhood. Causality remains intact. No observer sees effects arriving before causes. The universe permits separation without contradiction. This distinction between local motion and global geometry is subtle, and it matters immensely, because it means that faster than light is not a single idea. It is a family of ideas, some forbidden, some tolerated, some deeply ambiguous. And that ambiguity is where imagination and mathematics begin to blur. If space itself can expand faster than light, then could it also contract? Could it be reshaped? Could distance be compressed ahead of a traveler and expanded behind them, allowing effective superluminal travel without local violations? These questions are not science fiction in origin. They arise naturally from the equations that describe spacetime. Certain mathematical solutions suggest that spacetime can, under specific conditions, be arranged in exotic ways. Not easily, not cheaply, but theoretically. Regions where distances behave strangely, where the geometry itself does the moving. In these constructions, nothing locally exceeds the speed of light. No particle breaks the rule, no signal cheats. And yet, globally, an observer could traverse vast distances in arbitrarily short external time. It sounds like magic because it bypasses our intuition about motion. But it is deeply constrained by energy requirements, stability conditions, and quantum effects that may forbid it in practice. Here's the crucial point. Physics allows you to write down the idea, but nature may refuse to instantiate it. That refusal is important. Every time physicists try to push these solutions closer to reality, new problems surface. Energies that must be negative, quantum instabilities that explode. Feedback loops that collapse the structure before it can function. The universe seems to tolerate the idea, but not the execution. This pattern repeats across multiple proposals. Signals that appear to arrive faster than light turn out to rely on prearranged correlations. Quantum entanglement, for example, produces correlations that are instantaneous across distance, but they cannot transmit usable information. No message can be sent. No choice can be communicated. The universe allows coordination without communication. Again, the limit is not speed, it is influence. Any mechanism that would allow deliberate control to outrun light runs into resistance. The math twists, the energy diverges, the system destabilizes. The universe quietly withdraws permission. What's striking is how consistent this behavior is across wildly different approaches. Geometry, quantum mechanics, cosmology, all converge on the same outcome. Apparent shortcuts are allowed. Genuine causal violations are not. This convergence suggests something deeper than coincidence. It suggests that the speed of light is not an arbitrary parameter, but a structural feature, a keystone. Remove it, and the arch collapses. And yet, the universe does not advertise this openly. It does not label the boundary. It lets you approach it from many directions, learning the same lesson repeatedly. You can bend space, but not command it freely. You can correlate distant systems, but not control them instantaneously. You can approach the speed of light endlessly, but never cross it. Each near miss reinforces the same message. The universe is permissive, but not careless. This is where faster-than-light ideas reveal their true value. Not as engineering goals, but as stress tests. They probe the integrity of reality. They ask what breaks first: geometry, energy, causality, or consistency. So far, consistency always wins. which raises a final, uncomfortable possibility. What if the speed of light is not the fastest thing in the universe, because nothing faster exists, but because nothing faster can be allowed to exist in a universe that wants to remain logically coherent? That reframes the question entirely. It stops being about engines and particles and starts being about rules, not imposed rules, but emergent ones. The kind that arise when you demand that every observer, everywhere, can agree on what happened. And that brings us to the last edge of the problem, the place where physics stops offering mechanisms and starts offering meaning. Not poetic meaning, structural meaning. Why this universe, and not one where faster-than-light influence is normal? That question doesn't ask how to break the limit. It asks why the limit exists at all. And that is where the story is heading next. Nature allows uncertainty, but not inconsistency. It allows correlations, but not controllable influence. It allows mystery, but not logical self-destruction. This balance is delicate, and it appears to be enforced everywhere at every scale. Even hypothetical constructs that seem to allow time loops, closed time-like curves, are plagued by instability. Tiny perturbations grow uncontrollably. Quantum effects destabilize the geometry. The universe appears to sabotage these configurations before they can become operational. Not through a law written in bold letters, through dynamics, through feedback, through collapse. It's as if reality is self-correcting. Whenever a pathway threatens to undermine causal order, the conditions required to maintain it become physically unreasonable. Energies diverge, systems tear themselves apart. The solution remains on paper, never crossing into existence. This behavior is so consistent that some physicists have proposed an informal principle: chronology protection, not as a moral stance, but as an observation. The universe seems to guard its own timeline. And once you see that, the speed of light takes on a new role. It is no longer the fastest thing. It is the boundary of agreement. Inside that boundary, all observers can agree on cause and effect. Outside it, agreement dissolves, and so the boundary remains unbroken. This reframes faster-than-light travel not as a technological challenge, but as a philosophical impossibility, unless reality itself is willing to abandon consistency, which raises an unsettling thought. If the universe enforces this limit so rigorously, not because it must, but because it cannot function otherwise, then the speed of light is not an obstacle placed in our way. It is a condition for existence. And that leads to the final layer of the problem. The realization that what feels like a frustrating constraint may actually be the reason the universe is navigable, understandable, and stable enough for observers like you to exist within it at all. That realization doesn't answer the question, but it changes what the question means. And that is where we're headed next. Once you understand why faster-than-light motion threatens causality, a strange pattern emerges in the history of physics. Again and again, scientists encounter phenomena that appear to outrun light. Headlines flare, assumptions tremble. For a moment, the boundary looks cracked, and then, quietly, it seals itself again. These episodes are not failures, they are stress tests. One of the most seductive illusions comes from something called phase velocity. Imagine a ripple moving across a long rope. Individual points on the rope move slowly, but the pattern itself can sweep across faster than any single segment. In certain media, the crest of a wave can travel faster than light without carrying energy, matter, or information with it. At first glance, this looks like a loophole. Something is moving faster than light, but when you examine it carefully, nothing meaningful is being transmitted. No message arrives early. No cause outruns its effect. The universe allows the appearance, but blocks the consequence. The same happens with group velocity in carefully engineered conditions. Under exotic setups, the peak of a pulse can exit a medium before it fully enters. It feels like cheating. But when you track where the information actually is, the point where the signal becomes distinguishable, it never exceeds light speed. Once again, the boundary holds. Astronomy offers its own illusions. When jets erupt from distant galaxies, their motion across the sky can appear superluminal. Parts of the jet seem to race ahead faster than light itself. For a moment, the universe looks careless. But this is geometry, not violation. When objects move near light speed at just the right angle toward the observer, projection effects distort timing and distance. The apparent speed inflates. The true speed remains safely below the limit. Perspective creates the illusion. Reality stays consistent. Even expansion itself plays this game. Distant galaxies recede from one another faster than light due to cosmic expansion. This sounds catastrophic until you realize that nothing is moving through space faster than light. Space itself is stretching. No signal outruns causality. No information leaps ahead. The boundary survives, reinterpreted rather than broken. These examples matter because they reveal something subtle. The universe does not forbid things from looking faster than light. It forbids things from acting faster than light. Every time a scenario approaches that threshold, a technicality intervenes. Energy flow disappears. Information fails to transmit. Frames of reference dissolve the illusion. Expansion reframes motion. The pattern is unmistakable. Reality tolerates deception. It does not tolerate contradiction. This distinction becomes crucial when examining one of the most misunderstood quantum phenomena: entanglement. Entangled particles exhibit correlations that appear instantaneous, regardless of distance. Measure one here, and the other response there. No delay. Einstein famously called this spooky action at a distance, and for good reason. It feels like faster than light influence. But again, control is missing. You cannot choose the outcome of a quantum measurement. You cannot encode a message. The correlation is revealed, not sent. No usable information crosses the gap. Causality remains intact. Entanglement flirts with the boundary and stops. Even when experiments push quantum systems to extreme limits, the same restriction holds. The universe allows non-local correlation, but not non-local communication. Meaning remains local. Order remains protected. This is not coincidence. It is structure. At this point, the idea of something truly faster than light begins to feel less like a hidden breakthrough and more like a category error. You are asking whether the universe can violate the very rules that allow questions to be asked coherently in the first place. And yet, the discomfort remains. Because physics has surprised us before, boundaries that seemed sacred have fallen. Absolute space vanished. Absolute time dissolved. Determinism cracked. Why should this limit be different? That tension is not ignored by modern physics. It is actively investigated. Theoretical frameworks explore tachyons, warp metrics, wormholes, mathematical constructs that hint at superluminal shortcuts. But every time these ideas approach physical implementation, something goes wrong. Instabilities arise, energies diverge, quantum effects sabotage the geometry. It is as if the universe allows the idea, but refuses the execution. This leaves you in an unsettling place, not knowing whether faster-than-light travel is forbidden because it is impossible, or because it is incompatible with the universe that can remember its own past. And that distinction matters, because if the limit is merely technological, it invites conquest. But if the limit is structural, it invites humility. That is the question now hovering quietly beneath everything else. And answering it requires stepping back even further, not into equations, but into what it means for reality to have rules at all. That's where we go next. At some point, the question stops sounding technical and starts sounding existential. Not in a poetic sense, but in a structural one. You begin to realize that the speed of light is woven into far more than motion. It sits quietly at the center of how reality decides what is real, because physics is not really about objects. It is about events, things happening, moments that can be agreed upon, measured, compared, remembered. And for events to exist meaningfully, there must be a consistent way to say which ones influence which others. That consistency depends on information. Every physical interaction, every collision, every emission of light, every gravitational tug is a transfer of information. Something here affects something there. But if information could arrive before it was sent, the concept of affect itself would collapse. Influence would lose direction. This is why the speed of light shows up everywhere, even where light itself does not. It governs how quickly gravity propagates. It limits how fast forces communicate. It defines how observations synchronize. It is not a property of light. Light is just the messenger that reveals it. Think about how you know something happened. You see it, you hear it, you detect a signal. All of those processes involve information traveling toward you. Your knowledge of reality is always delayed, always local, always constrained. That delay is not a flaw. It is the price of coherence. If information had no speed limit, every observer could instantly access every event. There would be no perspective, no causality, no uncertainty. Paradoxically, there would also be no structure. Everything would collapse into a single, undifferentiated present. The universe avoids this. Instead, it parcels reality into causal regions, past light cones, future light cones, domains where influence is allowed, and domains where it is forbidden. These are not arbitrary boundaries. They are the scaffolding that makes physics possible. Inside your light cone, events can affect you. Outside it, they cannot. Yet, that separation allows the universe to evolve without contradiction. And faster-than-light influence tears straight through that scaffolding. It does not merely bend the rules. It erases the distinction between inside and outside, between before and after. Once that happens, the universe loses its ability to tell a consistent story about itself. This is why attempts to imagine in superluminal travel always feel strangely hollow. They focus on distance, on engines, on shortcuts, but they ignore the deeper cost. The cost is not energy, it is meaning. Because once information outruns causality, measurement stops making sense. Experiments lose reproducibility, predictions lose stability, science itself dissolves. The universe seems to know this, not consciously, of course, but structurally. The equations of physics conspire to prevent scenarios where observation and influence become disconnected. Whenever such a scenario approaches physical reality, something intervenes: instability, randomness, infinite requirements, or outright impossibility. This pattern has led some physicists to a quiet suspicion that causality is not a rule imposed on the universe, but an emergent requirement for any universe that can host observers at all. In other words, if faster-than-light influence were allowed, there might be no one left to notice it. This reframes the original question yet again. You are not asking whether something can go faster than light. You are asking whether reality can survive without a shared ordering of events. And the answer increasingly seems to be no, which makes the speed of light feel less like a barrier and more like a stabilizer. A tuning constant, a value that holds the universe together just tightly enough to remain intelligible. This doesn't mean the universe is simple, it means it is constrained. And constraints, in physics, are rarely arbitrary. They are often the only thing standing between order and collapse. That realization doesn't close the door. It changes the room you're standing in. Because once you see the speed of light this way, the real mystery is no longer whether it can be broken. The mystery is why the universe chose this structure instead of any of the countless others it could have adopted. And answering that takes us beyond limits and into origins. Once you accept that the speed of light is woven into causality itself, a new kind of curiosity emerges. It is no longer about brute force. It is about loopholes. If you cannot outrun the universe, maybe you can go around it. This is where imagination becomes dangerous in the best possible way. Physicists have spent decades asking a quieter question, not, how do we go faster than light, but, can space-time itself be arranged so that the journey becomes shorter? If distance is the problem, perhaps distance can be folded. This is where ideas like wormholes appear. At first glance, a wormhole feels like a clever hack. Two distant regions of space connected by a shortcut, like bending a sheet of paper and poking a hole through it. No object locally exceeds the speed of light. Nothing technically breaks the rule. You simply arrive sooner because the path itself is shorter. It sounds elegant, almost polite. But this elegance hides a problem that only reveals itself when you slow down and look carefully. Wormholes are not just tunnels through space. They are distortions of space-time so extreme that they demand conditions the universe seems unwilling to provide. To keep a wormhole open, its throat must resist collapse under its own gravity. That resistance requires negative energy, not just low energy, but energy that behaves in the opposite way of everything you have ever touched. Negative energy is not science fiction. Tiny hints of it appear in quantum effects, like the Casimir effect, where vacuum fluctuations behave in strange, counterintuitive ways, but these effects are microscopic, fleeting, and fragile. They cannot be scaled up without tearing the underlying framework apart. Every serious calculation points to the same conclusion. If you try to stabilize a wormhole large enough for anything meaningful to pass through, the universe pushes back hard. Either the energy requirements become infinite, or the structure collapses faster than it can be used. And even if, hypothetically, as you solve that problem, another one waits patiently behind it: time. Because once a shortcut through space exists, a shortcut through time is never far behind. If one end of a wormhole experiences time differently than the other, the tunnel becomes a time machine. Signals can loop back into their own past. Causes can arrive after effects. The logical order of events begins to unravel. This is not a side effect. It is a direct consequence. General relativity does not forbid time loops outright. It tolerates them mathematically. But the moment you allow them physically, paradoxes proliferate. Not narrative paradoxes, but structural ones. Situations where the equations no longer have stable solutions. Once again, the universe responds the same way it always does. It destabilizes the scenario. Tiny fluctuations grow uncontrollably. Energy diverges. Quantum uncertainty amplifies instead of averaging out. The very tools used to describe the system stop agreeing with one another. This recurring pattern has led to an idea sometimes called chronology protection. Not a law, but a tendency. A sense that the universe actively prevents situations where cause and effect lose their meaning. Not because time travel is dramatic, but because it is incoherent. And this pattern extends beyond wormholes. Consider hypothetical particles that always move faster than light, tachyons. On paper, they are allowed by certain equations, but the moment you try to interpret what they would mean physically, everything breaks. Their energy becomes imaginary. Their behavior reverses under observation. Their existence destabilizes the vacuum itself. They do not merely travel faster than light. They undermine the notion of a stable ground state. A universe containing them would decay instantly into something else. So again, the universe chooses coherence over possibility. Even quantum entanglement, often misunderstood as faster-than-light communication, obeys this rule. Entangled particles share correlations that appear instantaneous, but those correlations cannot transmit usable information. No message outruns light. No cause leaps ahead of its effect. The universe allows strangeness. It does not allow shortcuts that rewrite logic. And this is where the question begins to feel different. Because at every turn, wormholes, exotic matter, tachyons, entanglement, the universe seems willing to flirt with the idea of faster-than-light behavior, but never commit. It gestures toward it, then pulls back just before coherence is lost. Almost as if the boundary is not a wall, but a tension. Push too hard and the structure snaps. This does not mean the universe is conservative. It means it is consistent. And consistency, once you see it this way, starts to feel like the deepest lore of all. The deeper you go, the clearer it becomes. The speed of light is not guarding motion. It is guarding meaning. And the next step in this story is realizing how deeply that guardrail shapes not just physics, but perception itself. By now, the question has shifted so many times that it barely resembles its original form. What started as a curiosity about speed has become something quieter and heavier. You are no longer asking whether something can outrun light. You are asking what it would even mean to do so in a universe that only exists because limits exist. This is the point where many explanations stop, satisfied with rules and prohibitions, but stopping here would miss the deeper reveal. Because the most unsettling part of this story is not that faster-than-light motion seems impossible. It is that the universe appears to be built in such a way that the concept itself dissolves the moment you try to take it seriously. To see this, you have to think about motion not as a line through space, but as a sequence of states. A thing is here, Then there, something changes, something else responds. Motion is not just distance over time. It is the linking of events into a narrative that can be agreed upon. That agreement depends on a shared structure of time. In everyday life, time feels universal. You assume that now means roughly the same thing everywhere. You imagine that events unfold against a single cosmic clock. This intuition is so strong that it feels almost biological. But it is wrong. And the speed of light is the reason it is wrong. Once signals take time to travel, simultaneity becomes local. Two events that appear simultaneous to you may not be simultaneous to someone moving differently. There is no master clock ticking behind the universe. There are only clocks, each bound to their own path through space-time. This is not philosophical. It is measurable. Satellites experience time differently than clocks on Earth. Particles moving near light speed decay more slowly than identical particles at rest. These are not edge cases. They are confirmations that time itself bends to accommodate the light speed limit. Now imagine what faster-than-light communication would do in this context. If a signal could arrive before light, it would not just arrive early. It would arrive before the ordering of events had settled. It would slice across different definitions of now, creating contradictions between observers that cannot be reconciled. One observer would see a cause precede an effect. Another would see the effect precede the cause. Both would be correct within their frames. There would be no higher authority to resolve the disagreement. Reality would fracture into incompatible narratives. This is why the universe treats the light speed limit not as a speed cap, but as a sorting mechanism. It organizes events into a structure where disagreement can exist, but contradiction cannot. Different observers may see different orders, but none will see an effect without a cause inside their own light cone. Faster-than-light influence breaks that guarantee, and this is where the idea quietly collapses under its own weight. Not because engines fail or energy runs out, but because explanation fails. You can no longer say what happened, when it happened, or why it happened, not in a way that all observers can agree on. Physics stops being predictive. It becomes a collection of incompatible stories. The universe seems unwilling to pay that price. What is remarkable is how often this boundary appears not as a hard prohibition, but as a soft refusal. Every time a theory edges too close to violating causality, something intervenes, a divergence, an instability, a requirement that cannot be met without infinite resources. It is as if the universe allows you to approach the edge, to glimpse what lies beyond, but never to cross it. This pattern suggests something profound, that the speed of light is not merely a constant measured by experiments, but a constraint that shapes what kinds of universes can exist at all. A universe without a maximum signal speed might be possible mathematically, but it would not be stable, it would not be coherent, and it would almost certainly not be observable from the inside. Which brings the question back to you. You are an observer. Your thoughts unfold in time. Your memories depend on cause preceding effect. Your understanding relies on a world that does not contradict itself from moment to moment. The same limit that frustrates your dreams of faster-than-light travel is the limit that makes experience possible in the first place. And once you see that, the question stops feeling like a challenge to overcome. It starts to feel like a clue. Because the strangest thing we have found in space may not be a particle, or a wave, or a cosmic structure at all. It may be the realization that reality is held together by but about humility, scale, and what it means to exist in a universe that chose coherence over freedom. We're almost there. At this stage, it becomes impossible to ignore a quiet pattern that runs through all of human exploration. Again and again, we encounter limits, and almost every time, our instinct is the same. Assume the limit is temporary, a misunderstanding, or a failure of imagination. The speed of sound once felt absolute. No object could outrun it, until engines did. The atmosphere itself seemed to impose a hard ceiling, until aircraft tore through it. Even gravity once felt like an unbreakable prison, until rockets made orbit routine. History trains us to distrust boundaries, so when light appears to stand in the way, it feels familiar. Another wall waiting to be climbed, another rule begging to be rewritten. But this time, something feels different. Every previous limit was local. The speed of sound depended on air. Gravity depended on mass and distance. Escape velocity depended on planetary scale. These were environmental constraints, not structural ones. They restricted motion, but not logic. The speed of light is not like that. It does not depend on medium. It does not depend on source. It does not even depend on the observer in the way most quantities do. Everyone, no matter how they move, measures the same value. That alone should raise suspicion. Nature rarely hands out absolutes without reason. This is why every serious attempt to treat the light speed limit as just another barrier eventually runs aground. The equations do not resist gently. They resist catastrophically, as if the universe is saying, this is not negotiable. What makes this unsettling is not that faster than light travel appears impossible. It is that the impossibility feels necessary. You begin to sense that the limit is doing work behind the scenes, holding events together, preserving order across vast distances, allowing cause and effect to survive relative motion. Without it, the universe would not merely behave strangely, it would behave incoherently. And incoherence is lethal to explanation. This reframes humanity's role in the story. We are not outsiders knocking on the universe's door, trying to hack its rules. We are products of those rules. Our brains evolved inside a causal structure where effects follow causes, where signals take time, where now is local but stable enough to build memory. A universe without that structure might exist on paper, but it would not give rise to observers who ask questions about it, which leads to a subtle inversion of the original problem. Instead of asking why faster than light travel is forbidden, you start asking why the universe is built in a way that forbids it. Why this structure and not another? Why a cosmos that values coherence over convenience? The uncomfortable answer is that this structure may be the minimum requirement for a universe that can know itself. Too much freedom, signals without delay, effects without order, and reality becomes untraceable. Too much rigidity, and nothing changes at all. The speed of light sits precisely at the balance point between chaos and stagnation. It allows the universe to be dynamic without becoming contradictory. From this angle, the limit no longer feels antagonistic. It feels protective, not protective of us, but of the narrative itself, of the ability for events to mean something, of the possibility that the universe can tell a story, one where beginnings lead to middles, and middles lead somewhere coherent. This is why the most honest answer to the original question is also the least dramatic. It is not that the universe has failed to reveal something faster than light. It is that the universe may not be able to remain a universe if such a thing were allowed to exist. And once that thought settles in, the obsession with outrunning light begins to fade. In its place appears a quieter curiosity, not about how to escape the rules, but about why these rules are so carefully tuned in the first place. That question does not ask for speed, it asks for understanding. And that is where this journey finally begins to close. At the beginning, the question sounded simple, almost playful. Is there something faster than light, or is that impossible? It felt like the kind of challenge humanity has faced before, the kind that history tells us will eventually fall to better engines, smarter math, or a clever shortcut through the rules. But the journey changed the question. Along the way, speed stopped being just about motion. It became about information, about causality, about the fragile agreement that allows one event to follow another in a way that can be shared, tested, remembered. Light was no longer a beam racing through space, but a quiet boundary holding reality together. The closer we looked, the clearer the pattern became. Every attempt to outrun light did not merely fail. It unraveled the very concepts needed to describe success. Before engines broke, explanations broke. Before distances collapsed, meaning did. What felt like a limit imposed on us revealed itself as a condition that made us possible. Because a universe without a maximum signal speed would not just be faster, it would be incoherent. Effects could precede causes. Observers could disagree in ways that no experiment could reconcile. The story of reality would fracture into incompatible versions, none of them stable enough to endure. And yet, this is not a story of restriction. It is a story of balance. The universe could have been slower, more rigid, frozen into predictability. It could have been faster, more permissive, collapsing into paradox. Instead, it chose a narrow path between chaos and stillness, a structure where change is possible, but order survives, where exploration exists, but not at the cost of coherence. The speed of light is not the fastest thing we can imagine. It is the fastest thing reality can tolerate. Seen this way, the question transforms one last time, not into frustration, but into humility. The realization that some limits are not walls to be broken, but pillars quietly holding everything up. That the universe is not daring us to escape its rules, but inviting us to understand why they are there. And perhaps that is the strangest thing we have found so far. Not a particle that outruns light, not a shortcut through spacetime, but a boundary so fundamental that crossing it would erase the very idea of before and after, and with it, the possibility of knowing anything at all. So you don't end this journey wondering how to go faster. You end it appreciating the fact that anything can move, connect, or make sense in the first place. And in that quiet understanding, the universe doesn't feel smaller. It feels, somehow, more complete.